Hi, can you believe it? We're already in Chapter 9. Section 9.1 claims about two proportions. So Chapter 9 is going to be very similar to Chapter 8. Claim about a mean, claim about proportions, etc. We'll still write down the claim, H1, H sub O, draw the little picture with the bell-shaped curve, look up the critical values. So most of it's the same, but what's different in this chapter is you've got two groups instead of one. Oh, as I was just saying. So in this section, you have two independent samples. So that could be the percent of women that wear pink shoes compared to the percent of men that wear pink shoes. So in other words, if a woman wears pink shoes, that does not have an effect on whether a man wears pink shoes. They're independent. So you'd have sample 1, you need a sample size n1, and how many successes? When you divide that, that's the proportion. Sample 2, you would also have a sample size, and x2 is how many successes. Divide those two, you've got their proportion of success. And the claim is going to be about P1 and P2, just that, no numbers. So it's going to be something like test the claim that they have equal proportions. So P1 equals P2. So the test statistic, if you like to use formulas, you subtract the two p-values, P1 minus P2, from the two samples. You then divide by this, and this p bar is called the pooled estimate. So you would add the x's together, add the n's together. That's where p bar comes from. Of course, you could be using the calculator also, which I'll show you. So let's do an example. So for NBA players, LeBron James and Kobe Bryant, probably the two best players the NBA has seen. Who is a better three-point shooter? So we're going to have to reach into the past when they were both playing basketball at the same time. So I'm reaching way back to 2007-2008 season. Bryant, he made 150 three-pointers out of 410, so 36.6%. LeBron had 113 out of 359, which is slightly smaller, 31.5%. So you can look at these numbers and then see, oh yes, for that particular season, Bryant was better. But we're basically now saying over their professional career, who was better? So for the whole population of their basketball playing years, who was better? So test the claim they make the same proportion of three-pointers. So same means the claim is going to be P1 equals P2. The H1 cannot have an equal, so it's going to be that they're not equal, and that means it's a two-tailed test. And H sub O always has P1 equals P2. In here, I just said test the claim. I didn't say what level of confidence to use, so as a default, use 95%. So that means alpha equals 0.05. Then draw the little picture, and from table A2, get the critical values. 1.96 and negative 1.96 are the most common ones that we use from table A2. And then you could do the formula. So you would subtract P1 minus P2. Oh, I forgot my little subscript. That should say P1 and P2. And then for this 0.342, I added the 150 with the 113. That's the numerator. Then I added 410 and 359. That's the denominator. And that's where the 0.342 comes from. And then 1 minus that would be the 658. So this would be divided by Bryant's 410 attempts. And then the same thing is divided by James's 359 attempts. And I get a 1.487. So you could also use the calculator if you go to stat, tests, and then the two proportion z test. And then you just put in their information. 150 and 410 was Bryant. 113 and 359 is James. And then make it not equals. And the calculator says you should have gotten z equal to 1.490. Now on the calculator, it's actually more accurate than me doing this formula, because on this formula, I've rounded everything to 3 decimals. So that means that my third decimal could be off. The calculator uses 13 decimals in its brain. So using the calculator is not only easier, faster, more fun, and more accurate. So that would be the test statistic. Now a 1.49, that would land right about here. And when it lands in the middle, that means that we did not prove anything. So we cannot say they're equal, we cannot say that they're not equal, we just did not prove anything one way or the other. What about the confidence intervals? So when you have two groups, you could have a confidence interval, but it's going to be like this. P1 minus P2 is somewhere between, and then I just made up these numbers, 0.20 and 0.25. So if you're subtracting P1 minus P2 and you get at least a 0.20, that means the P1 has to be bigger than the P2. Because if you subtract two numbers and you get a positive, it has to be the big number, P1, minus the small number, P2. So in this case, this interval would say that group number 1 has at least 20% more success, or 20% higher success rate. So this is what the formula looks like, and here's how you get the error if you want to use the formula. So this would come from table A2. You plug in the P1 in the Q1, the P2 in the Q2, etc. That's how you get the error. Next example, who's more likely to pass one of my classes, a statistics student or a calculus student? So I have many years of statistics and calculus students, 626 stat students, and 530 got a C or better. During that same period, I had 505 calculus students, 359 who got a C or better. So for statistics, when you divide the two, you can see there's about almost an 85% success rate, 84.7% success rate. For calculus, when you divide their two numbers, 71.1% success rate. So instead of using the formula, I'm going to use the calculator. So go to Stat, go over to Test, and then to Proportion Z interval. Type in the numbers for group number 1, type in the numbers for group number 2, and I'm using 95% confidence level. And then it gives me the confidence interval, which is going from 0.087 to a 0.184. So that means group number 1 has a better success rate than group number 2, and it's better by at least 8.7%. So statistics students have a higher passing rate by at least 8.7. It could be as high as 18.4, but it's at least 8.7 higher success rate. Good job, statistics students. So, when will we get fail to reject with a confidence interval? Suppose this was group number 1, 80% success rate, group number 2, 78% success rate, and then I make the confidence interval, still using 95% level of confidence, and then I get this, negative 0.032 to a positive 6.8%. So this is a case where we proved nothing. That would be like getting failed to reject if we did the hypothesis test. Because the two sides do not agree. One side says you get a negative. So that means P1 is the smaller number, P2 is the bigger number. But then this side says you get a positive, which means P1 is the bigger number and P2 is the smaller number. So this side, when it's negative, says P1 is smaller. This side, when it's positive, it says P1 is bigger. Well, P1 can't be both bigger and smaller, so that means we proved nothing. So if there's a negative on one side and a positive on the other side, that's the same as fail to reject.